Hello everyone and welcome back. Last time we started looking at section 25, the reflection of light mirrors, and we're going to continue with that today. Last time what we saw was that when a ray of light struck a flat mirrored surface, it reflected, and it reflected according to the law of reflection. If we define the angle between the incoming ray and the normal line, so the normal line is the line that's perpendicular to our surface, the angle between the incoming ray and the normal line, we'll call that theta sub I, the incident angle. The ray reflected off of the surface with an angle we'll call theta sub R, that's the reflected angle, and again the reflected angle is the angle between the reflected ray and the normal line. The law of reflection told us that the incident angle was equal to the reflected angle. In other words, theta sub I equals theta sub R. And one more thing, when the ray comes in, it reflects in the same plane as the incident ray. So if, say, I have a flat surface on a table or something and a ray comes in this way, it reflects back out in the same plane as the normal line and the incident ray. It doesn't come in this way and then reflect off that way, or something like that. The incident ray, the reflected ray, and the normal line all in the same plane. Very good. What we're going to do today is take a look at what happens when we have reflection off of a curved surface, a curved mirror. Well, let's imagine that we have some curved surface, maybe like that. Remember, the cross-hatching shows us the back side of the mirror. And we have a ray that comes in and strikes our surface. Well, how can we figure out the way it reflects if we don't have a normal line? How do we make a normal line to a curved surface? Well, it's really very easy. The first thing we do is we draw a tangent surface, or in two dimensions, just a tangent line, to the curved surface at the point of contact of the ray. So where the ray touches, right here, I'm going to draw a tangent line. In other words, a flat line that kind of just matches that curved surface right in the area, right in the neighborhood of that point where the ray is touching it. So I draw a tangent line to the surface right at that point. So something like that, just tangent to the surface at that curved, tangent to the curved surface of the mirror. Then, once we have a tangent line, we can define a normal line. So a line that is then perpendicular to that tangent line, and there we have the normal line that we can use to apply the law of reflection. This ray will then reflect off in the direction described by the law of reflection. So we have an incident angle, a reflected angle, theta sub I is theta sub R, theta sub R equals theta sub I, and again they're going to be in the same plane. The ray comes in, reflects out, again in the same plane as the incident ray and the reflected ray. Very good. This could be either a surface that is curved this way or a surface that is curved in the opposite way, kind of like this, so that we have a ray coming in like this. Again, we define a tangent line, but now the tangent line is kind of looks like it's on the other side of the surface, so to speak. But we can still define the tangent line, and then from that the normal line, and the ray will then reflect, again according to the law of reflection. These two different kinds of curvatures, where the curvature looks in this direction and the reflected surface is on the outside of the curvature, we call this a convex mirror. While this way, when we're on the inside of the curve, we call this a concave mirror. Just a simple way of trying to remember which one's concave, which one's convex. If you think about a cave in a rock, in a hillside or something, a cave goes in this way and you go inside the cave. So if you think of concave, this is like a cave that you're going in. A vex Well, I don't know what a vex is. It doesn't work that way. So just think, well, it's either concave or it's the other one that's not concave. So there's concave mirrors and convex mirrors. Okay, great. The specific shape that we are going to be considering are called spherical mirrors. So what's a spherical mirror? A spherical mirror does not necessarily mean an entire sphere that makes up a mirror, but a part of a sphere. So imagine a spherical shape, and then we cut out a section of that shape that makes like a little bowl shape. That would be what we would consider a spherical mirror. The spherical mirror does not have to be an entire sphere, but just a part of a sphere. The reflective surface could either be on the inside of the sphere, so that, say, the back of the sphere looks like this, and we have this round bowl that's like looking on the inside of a bowl, or the back side of the mirror could be the inside of the sphere, and the reflective surface is then the outside of the sphere. So we can have concave spherical mirrors or convex spherical mirrors. A very, very simple example of something like this would just be a spoon. If you could get your hands on a shiny spoon, if you look on the inside bowl of the spoon, that would be a concave mirror. If you look on the outside part of the spoon, that would be a convex mirror. You need a nice shiny spoon to do that, or else you don't really see anything. We'll come back to that in a minute. All right, very, very good. Let's start with the concave mirrors and see what kind of reflection we get from those. Here is a concave spherical mirror, and we're going to assume that the outside of the sphere is the back side of the mirror. The inside of the sphere is the reflective part. If this is a section of a sphere, not the entire sphere, but a section of a sphere, we can still define where the center of that sphere is. This we will refer to as the center of the mirror. When we talk about the center of the mirror, we don't actually mean the middle point of the mirror itself. We mean the center of the sphere of which that mirror is an arc, or part of the surface of that sphere. There, I will refer to the middle area, so let's pick some middle point in the sphere, and exactly where it is doesn't really matter, but let's just pick some point towards the middle of the mirror, and connect the middle point with the center. I'm going to draw a line connecting these two. Okay, that's supposed to be a straight line. This line we will refer to on a regular basis, and this is called the principal axis. The principal axis of the mirror. Very good. Now, what we want to do is figure out how these mirrors, how this mirror, and then when we look at convex mirrors, how they reflect rays. We're going to look at a number of different rays and see what they do. And then we're going to try and figure out if they'll make an image or not, and what kind of properties those images have if they do make images. The first ray I want to talk about is, let's imagine we have a ray that strikes the mirror that passes through the center of the mirror. So remember, here's the center. We're going to talk about a ray that passes through the center. Then what does it do? One very important point, and let's keep this in mind, that once a ray passes through the center and then goes towards the mirror, it's going to reflect in some way. But the ray doesn't actually physically have to pass through the center as long as it comes from the direction of the center. So this ray over here, it's going to reflect off the mirror in some way. It doesn't matter if it started down here and went through the center to get up here, or if it started at a point up here and then went towards the mirror in the same direction. Let's keep in mind, when we talk about these rays, we mean a ray that goes through the center or comes from the direction of the center. It doesn't really matter which one. It's still going to reflect off the mirror in exactly the same way. So let's imagine we've got a ray that's coming from the center. It could have passed through the center or coming from the direction of the center, either one. That ray comes along, it strikes the mirror. What is it going to do? It's going to reflect following the law of reflection. So we need to figure out where's the normal line. To figure out the normal line, we need to draw in a tangent line. We draw in a tangent line to the mirror at this point where the ray is reflecting. We draw in our tangent line. We draw in our normal line. Now this is a very, very important point. Where is the normal line going to point? For a sphere, any point we choose on the surface, wherever we draw our tangent line, it doesn't matter where, the normal line is always going to point toward the center of the circle. This is a very, very important point. Normal lines to the tangents of a sphere will always point toward the center of the circle if we're looking at the normal lines on the inside of the sphere. If we need a normal line on the outside, the normal line will point away from the center of the sphere. So on the inside they point toward the center, and down below toward the center. On the outside they'll always point away from the center. Okay, it's a very important point, and we'll come back to this. So the normal line points towards the center. For a ray that passes through the center, what is the angle of incidence? The incident angle. It is 0 degrees. So what is the reflected angle? It is also 0 degrees. So how will the ray reflect? It's going to reflect right back on itself. So the ray will come in, strike the mirror, and come right back on top of itself and go right back toward the center, perhaps through the center, or at least it's going toward the center. This is very much like a ray that we talked about last time for a flat surface. A ray that strikes the flat mirror at a perpendicular angle, in other words, right along the normal line, reflects right back on top of itself. Well, this is kind of the analogous situation for a curved mirror. If the ray strikes the mirror along the normal line, in that case, what we mean is from the center, it's going to reflect right back on itself. Very good. Let's take a look, and now keep in mind, this happens for any ray that passes through the center. A ray that goes in that direction will reflect right back on itself. A ray that goes in this direction will reflect right back on itself. A ray that goes up there will reflect right back on itself. It doesn't matter which ray it doesn't matter, sorry about that. It doesn't matter which ray we're talking about. All of the rays that pass through the center will always reflect back on itself. Very good. Let's take a look at another ray. Let's look at an incoming ray that is parallel to the principal axis. Let's see, how does that ray reflect?